audible?
Yes.
Okay. So, ma'am has given the brief introduction about the topic. So, I will start. Okay. शेयर कर लो बैठा रहे तू भाई So, I will start with the introduction to fractional calculus. So, fractional calculus is a different branch of calculus in mathematics. I think most of you are not aware from it, but you all of you are aware from the classical calculus, which have the basic derivatives of integer orders, mainly the natural number of order, the first order derivative, the second order derivative. Um, and all, then it arises the origin of this branch will arises from the mathematical curiosity that what will be the mean if we take the half derivative or like 1 by 3 derivative, 1 by 4 derivative of a function, then what will happen and what will be the mean of it. So, fractional calculus is the study of derivatives and integrals of arbitrary order. We can say that, and it generalizes the classical calculus to the non-integer orders or arbitrary orders um, for differentiation and integration. So, we will define the fractional derivative by this symbol where alpha is non-integer and phi can be any real number, positive real number. So this is the differentiation of f, fractional differentiation of f, this symbolize. And now we can use the fractional calculus branch in different fields. These are very basic fields because in viscoelasticity we use the traditional derivatives in material modeling, but now we can use the fractional derivatives. They will provide many more insight of this viscoelasticity modeling and capture the past history, which shows the better perception of it. And signal processing, so the fractional calculus helps to model a long memory and self-similar signals were found through it. So it is better to use fractional here. And also in diffusion and control system, we also use the classical derivatives. So the fractional diffusion equations model the system more accurately. You can search this type of research work, and try to find the use of fractional calculus in these fields. So, in a summary, fractional derivatives are non-local and contains memory property. What is the non-locality and memory property? So, the classical derivative uses the value of a function at a single point or or in its neighborhood. So, it is a local property, and a non-local operator depends on entire history of a function. So we will call any operator a non-local if it uses the uh, entire points of a function, entire values of a function. So so unlike the classical derivative, it does not consider instantaneous rate of change, but it will contain the whole memory fact of the function. So fractional derivative at a point depends on all previous values of the function. It is the memory property. So there is no any unified definition of fractional derivative till now. And so many mathematician provides different fractional derivative operators according to their requirement of problem and functions. And the Riemann-Leibniz derivative and the Capito derivative are more common and more usable fractional derivatives in different tasks. So we have provided the introduction of these two derivatives. We also consider these derivatives in our work. So these are they both are derivatives very similar kind of definition. So in equation 1 you can see the Riemann-Leibniz fractional derivative definition of order alpha, which is a fractional value between n minus 1 to n. N is a natural number here, and f is a continuous function. So RL is a Riemann-Leibniz symbol here, and alpha is the fractional order, and a to x is the integral limit, and fx is function, and this is gamma function, and this is the nth order classical derivative, and we take the integration from a to x of f, and this is the kernel of Riemann-Leibniz derivative. So we are talking about the memory property. Now you can see here that the fractional derivative at point x, the Riemann-Leibniz derivative, is containing the all values from the starting point of the domain f function, and we can take a according to fx. It is taking the all values from a to at that point x. So it is containing the all entire history values of that function. So it is depending on the past values of this function. This is the memory property of this Riemann-Leibniz derivative. Now Capito derivative definition is given here. It is slightly different from the Riemann-Leibniz. Here the derivative of classical derivative operator is outside from the integration, and in this Capito derivative it is on the f function only. So f should be here n times continuously differentiable, and it is defined as 1 upon gamma function of 1 n minus alpha and a to x. This is the kernel of Capito derivative which provide weights to that function, and again alpha is between n minus 1 to n, and gamma is the gamma function. So
हेलो
hello, yes
गुड
ma'am.
मॉर्निंग रमेश जी मुझे ये पूछना था कि ये जो गूगल फॉर्म भरना है उसकी कोई लास्ट डेट है क्या
Ma'am,
वो आपने
ma'am please mute yourself. So we can start. So Riemann and Capito derivatives model memory effects as you see in the definition. And this is useful in the data type which is dependent on the past values of the data, like time series modeling, recurrent neural networks which uses the time dependent data, and history dependent dynamics models, and all data which will related to their past values. So Capito derivative coincide with classical derivative more, making it easier to implement machine learning algorithm. So you can see from here, if we take fx as a constant, then we will get 0 here. So this will get, the fractional derivative of a constant function will provide 0. But in Riemann-Leibniz, it is not 0. So the Riemann-Leibniz derivative not 0 for a constant function, but Capito derivative is. And when we generalize these definition for alpha equal to 1, then Capito derivative will coincide with the fractional derivative, but Riemann-Leibniz will not. So these properties will make the Capito derivative more easier to implement in the task where classical derivatives are taken. And in machine learning algorithm and numerical solvers, the initial conditions like f dash 0 equal to what, and these initial conditions are always in a classical derivatives. So we found that we can directly implement the initial conditions in the Capito derivative by the ease of their definition. So It is easier to train models using backpropagation when derivatives behave similar to classical ones. That's why in designing fractional order neural networks, the Capito is preferred for simpler gradient computation. Now we will derive how can we apply fractional derivative on the mechanism of backpropagation. So we will start from the basic and simple optimization technique of gradient descent. So this is the formula is given here. Now we will see that how can the fractional derivative applied. So we just replace the normal derivative of f by the fractional derivative. So theta is update from here and gamma is the learning rate. So we will apply this on the neural network mechanism. So we can see the architecture of a simple with one hidden layer neural network. These are the output classes, output layer, which is the output neurons. This is the input layer and this is hidden layer. So we have only two matrices, W1 and W2 here. And to show the mathematical computation of it, we have taken the simpler architecture and just two weight matrices and as a parameters. So just the forward pass begin. T are the number of T is the number of samples here. We will do for the first sample here, and the again the same computation which I've done for neural network. Uh, and we will arrive f and g are activation functions here. So we will arrive the output of the output layer, which is OTI hat, and I is the number of classes. So W2 has the dimension of I and the hidden layer classes. That's why I is taken as indices. W2 has all the entries with I index. So n is the number of classes and I is goes from 1 to n. Now how the cross entropy loss will look like. This formula is showing here. The T is the training samples, I N are the classes, and this is the cross entropy formula for multi-class classification. And then we will show the gradient descent updation, fractional gradient descent updation for the weight parameters in this equation. I is for 1, 2 because we have two matrices, W1 and W2 here. So we can apply this fractional because L is a function of combination functions. So apply the fractional gradient on this whole function will create a computational burden. So we will just apply the classical derivative on L with respect to Wi's, and then take the fractional derivative of the last variable as a chain rule. So this is the one variable function, and we are taking the fractional derivative with respect to it, like we are taking the classical derivative of x with respect to x. So let's take x is the one variable function, and we have defined the capital derivative definition here for alpha equal to alpha is between 0 to 1, and we have taken a as 0 here. And by computing this integration, we have got that the fractional integration of x is x to the power 1 minus alpha upon gamma 2 minus alpha. So fractional derivative of loss will look like this, and fractional gradient descent algorithm formula will look like this. So this is different than the classical gradient descent, and you can see that this additional term will provide a degree of freedom to the backpropagation mechanism, because now we are not all dependent on the gradient flow. This will control the gradient flow in backpropagation by taking different alpha order between 0 to 1. We are on 0 to 1 to take simple steps first, and to derive the theoretical interpretation of this FGT algorithm, we have proved two theorems. The sequence is generated for the loss function by the updated weights. So it is monotonically decreasing, and there exists a point where it is converges. So it is monotonically decreasing, and it is converges. So it is converges to its minimum, and the loss function is greater than 0, so it is converges to a minimum point of L star. And the FGT and the second theorem for the order of convergence. So we have derived that the order of convergence is linear here, and it for any continuously differentiable function. So all the activation functions used in neural network architecture are continuously differentiable. So we will not get any trouble. And for alpha between 0 to 2, it has linear convergence. Alpha between 0 to 2, because this function will define only for this range. So the gradient descent also has linear convergence. Now we have found the results for the iris dataset classification using this new optimization FGT, optimization technique FGT algorithm. And we have derived the results for different order of alpha between 0 to 1 to check the dependency on alpha order of the learning of the neural network. So here the accuracy graph is shown here, and the loss is decreasing with respect to the order alpha for iris dataset classification. So you can see here for alpha is 0.4, we get the highest accuracy training, and lowest and smoother loss minimization according to POCs. So we can take that for 0.4 fractional order, it can be assumed as an optimized fractional order for the FGT algorithm for iris dataset for this particular dataset only. So we have taken this optimized fractional order, and then with this fractional order we have we compared our FGT algorithm on iris dataset with different optimizers, trending optimizers like ADAM, SGD, and RMS prop. So you can see here also the FGD algorithm is providing smoother loss minimization and highest accuracy achieving by this FGD algorithm. So we can suggest for this iris classification with 0.4 fractional order, we can get the better results than existing optimization techniques. Then we have test the model with test dataset, and the accuracy is highest for the FGD algorithm than other optimization techniques. So now we have applied a new technique which you introduced about this yesterday, the initial parameter selection using meta-heuristics. So meta-heuristics like genetic algorithm and PSO and Firefly algorithm explore the parameter space globally. You all know that. So we have a session of non-convex landscape, and try to get the minimum using different optimizers. There you have seen that if we are changing an initial point of for any optimizer, then the converging is differ. For non-convex landscape, we have many local minimas or saddle points. So the choosing of the initial point is very crucial, because it will affect our training procedure, and it will impact on our results. So to choose the best initial parameters, we have used the meta-heuristic algorithm rather than the random initialization. And well chosen initial weights will lead to faster and more stable convergence during training, especially for the non-convex loss landscapes. So we have taken three meta-heuristic algorithm, Firefly, PSO, and Grey-Wolf convergence. So we have tested this on our loss function. Then we arrive at the decision that the Firefly is behaving very nice on this loss function. So we have taken this meta-heuristic algorithm for the further computation of neural network. So this hybrid FGD is what we have taken meta-heuristic techniques for the initial point initialization of parameters, and this is the blue line is only for the FGD here. So we can see the convergence is faster. We're using the hybrid FGD, which has taken the meta-heuristics, and the accuracy is also higher by using this on this results is for iris dataset. We have already compared this with different optimizers, and 0.4 order has concluded. Then we will apply the hybrid FGD also. Then we have taken the comparison for iris dataset here in terms of the training accuracy and in terms of the training loss. And now this is the experiment on breast cancer dataset. We also derive the optimized order for the breast cancer dataset, and take the comparison of normal FGD and hybrid FGD for it. So it is also converging faster for the hybrid FGD and than FGD alone. So meta-heuristics are provide enhance and accelerating the training for the neural network classification. And again, we have checked on this mechanism on heart disease dataset to classify the heart disease on patients. So again, we can see the hybrid FGD behaving better than FGD using meta-heuristics. So we are on this. We can see, and loss is also minimizing faster against epochs than FGD alone. So by again on the house price data set, we have checked our FGD and hybrid FGD on RMSC error, and again the hybrid FGD is minimizing faster the RMSE. So we can arrive at that decision by checking on our algorithm on these benchmark data sets, that by using the meta-heuristic algorithm to select the initial point of the for this new optimization technique FGD, we can enhance our training mechanism and get better results. So this work is published in this Chaos, Solitons and Fractals Journal. You can go through it. And now we are doing these FGD algorithm on real life data set, which is a silicosis disease data sets. The description of the data has given here. So it is a lung image data set. So you can see these two images. You can differentiate between these two images, that this is a clean lung image, and this has the silica particles in the lungs, which has the silicosis. So this is the image of lungs of silicosis patient. So we have to classify this silicosis disease by using a deep CNN model and using the fractional optimization technique. So we have classified this and used the AUC metrics to evaluate our model performance. So the highest AUC have achieved for 0.8 order, and which is 0.95. So this is contributing that the fractional and alpha equal to 1 is showing the uh, traditional method of gradient descent. So we can see that using the fractional orders, it is better than the traditional methods, and we can get higher results and higher and better results from using the traditional one. So this is our classification graph of ROC curve. So this is all the work, and if you have any questions, you can ask me related to this work. Now Mukesh will introduce the fractional order filters in images processing to you.
Hello and good day to everyone. Myself Mukesh Delu, and I will discuss fractional order filters in image processing and their mathematical foundations and their real-world implementations. So, what is an image? Image is nothing but a matrix of pixel intensity value. So we can think of an image as a function with domain is pixel position and range in intensity value. So if we want to analyze the image, we look for the changes in pixel intensity, which indicates edges, boundaries, textures. So how to find changes in function? Changes in functions find by derivative of it. So uh, derivative measures how intensity changes across neighboring pixels. Also, to find derivative of discrete function, we use numerical approximation. As we know, images are discrete in nature and represented by matrices. So we need numerical approximation of derivatives and also need kernels to slide over the image to detect changes in intensity values. So kernel is nothing but a matrix of 3 cross 3, 5 cross 5, or you can say 7 cross 7. Okay, so what is fractional calculus? As Rinki ma'am discussed, fractional calculus is generalization of ordinary differentiation or integration to arbitrary non-integer order. If dnf upon dxn, you choose n is any integer, positive integer number, then it is ordinary differentiation. But if you choose n is 1 by 2, 1 by 3, like this, 1.5, like this, then this is non-integer, and we call this fractional differentiation. So there are some popular fractional differentiation definition available in state of the art. So first is Riemann-Liouville fractional derivative. As Rinki ma'am discussed, it is nothing but the non-integer order generalization of Cauchy integral formula for n integration, and this GL derivative is generalization of a limit formula, definition of a limit definition of the derivative, and we generalize it to non-integer order. Next one is Capito derivative. So you discussed basics about this derivative in previous slides. So I want to discuss about singularity of this derivative. As you can see is in equation 6, if we insert t is equal to tau, then it will become a singular, and that is a problem faced in image processing. So Capito-Fabio introduced a new fractional derivative in which he replaces they replaces the singular part by a non-singular exponential kernel, which is given in equation 7. This kernel has non-singularity. All the fractional operators are is non-local and have memory effect. Just like this ABC fractional derivative, Tangna and Belvano replaces this non-singular kernel by a Mittag-Leffler function. As you can see, Mittag-Leffler function is also non-singular. So as you can see, we need neighboring pixel information to analyze the image. For that, we need a memory effect, and a fractional derivative has memory effect. Okay, you want to compute the fractional, this ABC fractional derivative as t equal to 1. So it will integrate from 0 to 1. So it will take all the information of f from 0 to 1. So it has memory of all the neighboring pixels. Also, it is non-singular and non-local. So it is very helpful in image processing task. Okay. So this is the ABC fractional integral corresponding to this previous derivative. So here n is nothing but a normalization function, which is given in equation 11, or equation 10 represents the ABC fractional integration. So what are fractional order filters? So traditional image filters uses image order derivative, integer order derivative, like first order, like Sobel Privet uses first order derivative, and Laplacian uses second order derivative. But fractional order filters extend this concept to non-integer derivative. It will help us fine-tune and control overfitting and enhancing by adjusting the derivative order of alpha. If you are not getting good result for alpha is equal to 0.5, then you don't have to change the filter. You just have to put the another value of alpha. And if we are able to optimize this alpha, then it will become a very good filter. Why use fractional filter? As I discussed earlier, it has non-local, non-singular, and memory effect features. Also, it is good in achieves good balance between edge sharpness and noise suppressions. And nowadays, it is widely used in medical imaging, texture analysis, and bioimages processing. Okay, so how to generate a fractional order filter? So first of all, we have to find numerical approximation of the fractional derivative. So equation 12 is the essential equation for extending fractional operator in image processing. So this equation shows the numerical approximation of fractional order derivatives, or you can say operators, where beta naught, beta 1, beta 2, beta 3 are sequential coefficients. By finding these beta 1, beta 2, beta 3, we can find these two kind of structure, mask 1 and mask 2. These masks are for edge detection tasks. For denoising task and other tasks, you will have different structures of masks. So mask 1, FXV means mask in X direction. It will detect edges in X direction. And FYV will detect edges in Y direction. So next is approximations. So first one, we are using approximation of ABC fractional integration. First one is based on Grunwald-Letnikov approximation method. So equation 15 gives us the approximation. And by comparing with equation 12, we get this beta naught, beta 1, beta 2, beta 3. By using these beta naught, beta 2, beta 3 and inserting in these masks, we can generate fractional filters. Similarly, if you use middle point approximation for ABC fractional integration, we generate a different approximation, and which is mentioned in equations 16. And using this approximation, we get this beta naught, beta 1, beta 2, beta 3. Like these, you can approximate another other fractional operators available there, and you can find their corresponding beta naught, beta 2, beta 3, and their corresponding fractional order filters. Okay, so this is the example of a fractional order filter which is based on middle point approach based approximation and structures mentioned in mask 1. So fx is in x direction and fy in y direction. Okay, so we apply this filter in these images. These images are taken from BS DS500 dataset. So these are different images, and we apply this fractional operator, fractional filter on these images. As you can see, we take order of fractional is 0.873. You can see these filters detect almost all the edges, and also sharpens the edges, and it shows good results in edge detection tasks. Next, I will discuss modified fractional edge detection mask based on compass gradient. What is compass? Compass has 8 direction. So in a previous slide, we have mask in 2 direction, only X and Y. I want to mask in all 8 direction of the compass. So this study is presented in ICWT 2023 and is published in IEEE Digital Explorer. You can check it out. So what we are doing? So okay, first of all, there is something traditional Chris compass mask and Robinson compass mask. How to generate them? Just rotate, take a mask and rotate it by 45 degree. So you will get north direction, you will get northwest direction, you will get west direction, southwest, south, southeast, east, and northeast. You will get all the essential 8 compass direction. We generalize this Robinson compass mask to generate a fractional compass mask based on Robinson compass mask. So this is the just like M1, we take filter M1, then rotate it to 45 degree, then we get M2, then M3, M4, just like this. So what is PQR? PQR is nothing but coefficient beta naught, beta 1, beta 2. And we insert that coefficient in these filters and we get 8 filters. Just like that, for Chris compass mask, we get these 8 filter. Structure of Chris compass mask looks like this. Okay, this is looks like mask 2 structure, and this is looks like mask 1 structure. So we get these two masks, and we have value of P, Q, R, S, S, beta naught, beta 1, beta 2, beta 3. Okay. So this is the proposed algorithm. So first of all, you take the image, then apply the Gaussian blur for noise reduction. Then we get edge maps in all the 8 direction: east, northwest, north, northwest, etc. 8 the direction. Now we get 8 edge map. So we want to find intensity gradient. If we have two edge map, then we square them, sum them, and root them, and then get the intensity gradient magnitude. In this, we apply a different approach. We select a pixel position for all the 8 maps and find which map has maximum value at this particular position, and we take only the maximum value. So this intensity gradient, like east filter is not detecting some edges, but south filter is detecting that edge. So we don't miss any edges. After that, we did edge normalization to look it visually good. We convert it into 0 to 1. And then thresholding is applied for removing small objects or noise or unnecessary information in the edge map. So we first of all, we applied it on the BIPED data set. So as you can see, first image is original image, second is ground truth image, third one is image generated from robots, fourth is Previtt, next is Sobel, next is Laplacian of Gaussian at sigma 1.4, next is Kenny, next is Frichen, next is Sacher, next is Robinson image, next is Chris image. Now, last 4 images are from our proposed kernels. So, first image is improved Robinson, which is improved by GL approximation approach of ABC integration, ABC fractional integration. So, we use value of V is 1.85. For this image in last row and first column, we use improved Robinson, but we use here ABC approximation of ABC fractional integration using middle point approach. This is for V is equal to 1.63. Just like that, we are using here improved Chris with GL approximation of ABC derivative with V is equal to 1.69. Here we are using improved Chris with ABC fractional integration with middle point approach approximation with V is equal to 1.76. As you can see, all the 4 proposed kernels have sharper and smoother edge compared to other masks. Also, we check them by quality matrices. So for this, we use MSE, PSNR, SSIM, which is shows a similarity index, and EBIQA matrices. So as you can see, MSE should be lower, PSNR should be greater, and SSM I should be greater, and EBIQ is lower for better results. So as you can see, all of our 4 masks perform better results than these 9 traditional edge detector. Sorry. Okay. So next, we won't apply it on medical images. So we apply it for drive dataset example. Similarly, these are traditional masks. Now, last four masks are from our method. So as you can see, it shows a sharper and smoother edges, and it detects blood vessels uh, clearly, like that you can see in quality matrices. So it is performing better. We apply on HRF dataset also. You can see our methods proposes good results, and in terms of quality metrics, it is also uh, outperforming these traditional methods. Okay, so this study highlights the following thing. First is that by taking the advantage of fractional order, we can find a good age map because of its flexibility, and if we optimize this, we can get a more better age detector than this traditional age detector. Okay, and also these kernels have the potential to serve as promising alternative options for enhancing age information. I applied in on the medical imaging, but you can apply it in where ages are presented. Like you want to apply, you can apply it for fingerprint scanner. You can palm hand recognition system. You can apply it for uh, to find blood vessel in egg cell, and you can apply it many methods where ages are important. Thank you. Any questions and discussions are welcome. So kindly